Hello everyone and welcome to another National 5 course video, this time introducing surds and indices. So let's have a wee look at what's in this new unit then. So what we've got is we're going to take a wee look at what a surd is and how to simplify them. Essentially surds, by the way, we'll get on to what they are, but they're essentially just numbers. So this unit is pretty much about learning what to do with a whole new set of numbers. So we're going to look at how we can manipulate surds, multiply, divide, add, subtract with them. We're going to take a wee look at the rules as well for dealing with indices, which you've done a little bit of work of in previous courses. Think back to S2. You'll have looked at things like what x times x squared is and how that becomes x cubed and things like that. So that's where we'll start off, multiplying and dividing indices, bringing a power to another power, negative indices, fractional indices, and they're linked back to surds, and then the rationalising the denominator of a fraction. And essentially it's quite a short unit. We'll get it done over this week and next week, but it is essentially just a big list of rules that you need to learn. So let's take a little look at what a surd is. Now, a surd is to do with the square roots of numbers. So you can find the square root of a lot of numbers. You can take the square root of 16 and get 4, square root of 9 and get 3, and so on. But there are a lot of numbers that you cannot find the square root of exactly. It doesn't mean that the square root doesn't exist. Of course the square root exists, but you cannot find it exactly. So take for instance the square root of 3. The square root of 3, if you were to punch that into your calculator, and the calculator would possibly default to giving you square root 3 on the display when you hit equals. But actually if you hit the SD button, the display will fill up with a string of digits, and those digits are infinite. And there's another number actually that's a bit like that you'll recognise. You've worked with the value of pi before, and pi is approximately 3.14. And there's no exact representation for pi other than using a symbol. There's no fraction you can write it as. You can't write pi as a fraction. You can only write it as a decimal, but with an infinite number of places. Like you can't even write the 3.14 is not an exact representation of pi. Pi has an infinite number of decimal places, so it is what's called an irrational number. Well, these surds, these square roots of numbers that you cannot exactly find the square root of, they're irrational numbers too. And the reason why they're introduced in the Nat 5 course is because there are a lot of scenarios at National 5 where it is, or certainly in beyond that and in further maths, where it is better to work with the exact value than it is to work with an approximation for it. So if you're an engineer, for instance, designing some system, then you might not want numerical errors creeping in. So you might prefer to work with the square root of 3 rather than the approximation for the square root of 3, you see. So it's better to leave it with the square root sign than try and round it to 2 decimal places. So square root 3 is an example of a surd, right? So surds are irrational numbers written with a root sign. Let's take a wee look at this example here. Which of the following numbers are surds? Well, numbers that are surds, remember they're irrational. We can't find the value of them exactly. So take square root 2 for instance. That is a surd, right? And it is a surd because we can't find it exactly. We know it's maybe roughly, if I remember right, it's about 1.41, something like that. But we can't find out what it is exactly. So that is what's often referred to as an exact value. Okay. Square root 9 is not a surd. It's a number written with a root sign, but the actual value of square root 9 is 3. It's a whole number, so it's not irrational. We can actually find the square root of 9 to an exact value, so therefore it is not classed as a surd. 3 root 2, however, that is a surd. And the reason 3 root 2 is a surd, although it's a mixture of a surd and a whole number, the reason 3 root 2 is a surd is because a handy way to think of this is if you think of this as a multiplication, 3 times the square root of 2. Now, if square root 2 is an irrational number and is a surd, then 3 times the square root of 2 must be an irrational number 3 times as big. So therefore it is a surd. Okay, so that gives you a idea on how to identify what are surds and what aren't. Essentially, if you can take the square root of it to an exact value, like square root 9, then square root 9 is not a surd. Okay, it's all to do with what the actual numerical value of these representations are. So square root 9 is 3, but square root 2 we're not too sure about. It's got an infinite number of decimal places. Now, some of these are very common examples of how to use surds, particularly what you're asked about at Nat 5. So we've got a triangle, calculate the length of x, giving your answer as a surd. Right, so what are we to do with this? Well, it's a right angle triangle. To find the length of the longest side, so we'll use Pythagoras' theorem. X squared equals, so it's going to be 4 squared add 1 squared. Remember, when using Pythagoras' theorem, if you're finding the length of the longest side, you must add. X squared will then be 17, and so x is the square root of 17. Now, ordinarily, you'd grab the calculator and you'd go and work out what the square root of 17 is, and you would go and give your answer to 1 or 2 decimal places. But we have to give our answer as a surd, so we're not going to take it any further than that. That is our surd, and which is an exact value. Okay, the vast majority of these questions, in fact, if not all of these questions, will go into non-calculator papers. So I strongly discourage the use of a calculator during this topic. There are a couple of times where I'll let it go, but for a lot of the time, the more you try and force yourself to work without the calculator, the better you'll get on in the long run.